Hello everyone. So today's topic, it is a special topic which is very important for the competitive exams. Term symbols. So basically term symbols. It might be the name might be the different, but to explain in very short manner, it is equal to the electronic configuration. Okay. So what is the electronic configuration? Electronic configuration is the indication or index of the energy levels and the electrons which are present in the energy levels. Okay, so exactly term symbol is also do the same function. So in if for example, if I take hydrogen, what is the electronic configuration? It will be the one electron, so 1s1. Okay, so what it is, this 1s is the energy level and one electron is present in that. So term symbol is also explain the same information but about the valence electrons. Okay, valence electrons, that is the first difference. And the second difference, it is about the elements which are in pure form. Okay, or you can also explain for the molecules even if it is in the oxidation states with different oxidation states. Okay, electronic configuration can be explained for the different atoms in different oxidation states. The same thing, we are not going to use much for the elemental form. Of course we can do, but most probably we will be going to do the term symbols, usage of the term symbols mostly for the atoms which are present in the molecules and which are present in the oxidation states, different oxidation states. So if you can see, these are the ground state symbols or ground state term symbols of all elements. Okay, so this is the periodic table with ground state term symbols of all elements. So if you can see, it will be very overwhelming, but if you can spare the 10 minutes of time and you will get the all term symbols and why they are with the ground state, that will be very easy. So just pay attention for the next 10 minutes. So you will be going to write any term symbol for any element in any electronic configuration. Okay, so I hope you understand what is the importance of the term symbol. So it is basically electronic notation of the valence electrons. Okay, so how we going to express the term symbol, that we are going to see now. So expression of the term symbols, as you like, for electronic configuration we are going to follow Hund's rule. Okay, and based on the energy terms 1s, 2s, okay, and 2p, 3s energy levels, we are going to add the electrons, isn't it? So in the same way we are going to add up the energy levels, and based on the energy levels we are going to decide whether which is the ground level and which is the first excited level or higher energy level. So that will be going to decide by the energy. Okay, so as I told you, term symbol is the expression of the electron, especially valence electron, present in which of the energy level or in which of the orbital. So we are going to define the orbital, that is what energy levels, which is of the valence electron. So how we can express the energy of the orbital, especially based on the orbital angular moment. Okay, orbital angular moment as well as the electronic spin. So these two energies will combine together to give the energies of a particular orbital. Okay, so here the term symbol do the same thing. So this is what the expression from the spin quantum numbers Quantum numbers are the numbers which will explain the energy terms of the orbitals and spin and orbits, okay, based on the quantum numbers, okay, and the type of the quantum number. So S is the spin only quantum number, so L is the orbital quantum number, and J is the combination, so combination of spin and orbital quantum numbers. So a term symbol is going to have the spin quantum number value and the orbital quantum number value and total, okay. So this is the indication or symbol of the ground state term symbol, okay. So how to write, how to apply for a specific configuration. So if I say, let's say we'll take the simple or simplest electronic configuration, hydrogen, which is 1s1, okay. So total spin of the electrons that are present in the valency shell, so total spin will be, it will be plus half, because it is going to have only one electron. So S is the plus half, so 2 into half plus 1, so it is what, 2, okay. So this upper value, okay, or superscript is the value equal to 2. Next, L value, L is the orbital quantum number which is depends on the orbitals, okay. If it is s orbital, the L value will be 0, okay, as like orbital quantum number, that is what exactly same. If it is p orbital, it is 1. If it is d orbital, it is 2. If it is f orbital, it is 3, okay. So how we going to derive the orbital quantum number or the L value means, so let's take electron 1s1. So this electron is present in s orbital. So how many electrons? Only one electron that is present in the s orbital, whose value is L value, orbital quantum number value is 0. So if it is 0, it is equal to s. So the symbol will be capitals, okay. The L symbol will be capitals. So S, P, D, F, okay. If it is 4, it is G. So if it is capital, you must write capital S, okay. Then J value, so J is the combination of L plus S. So S is given 2 and L is with 0, so total will be 2. So this is what the ground state symbol of the hydrogen, okay. So I hope you understand the simplest one. Now we will be going to see, let's cross check whether what we have done the hydrogen ground state symbol. So generally for the ground state symbol you require this 2s plus 1 and L value. This is also sufficient. If they are asked even deeper, then you need to see whether J value need to write or not, okay. Most probably to your syllabus J value is not mandatory. You are going to deal with the 2s plus 1 and L value. See here, so hydrogen, it is doublet S, okay. So in that least value will be half, okay. That I will explain in the next example, okay. So now we will be going to consider one more example. So 2s plus 1. So let's take manganese in plus 2 condition. So what is the electronic configuration of manganese? It is 3d5 4s2. If it is in plus 2, this 4s 0. So the electrons which are present are only in d orbital, okay, only in d orbital, okay. So I am taking a weak field arrangement, okay. So here no ligands are given, so it is a weak field arrangement. I am just taking for the example, okay. So you can also take based on the environment also. So if this is the condition, total spin. So as the term symbol is the 2s plus 1 L and the subscript of J. So first 2s plus 1. So it is the total of the spin only quantum number. So plus up, plus up, plus up, plus up, plus up. So it is the 2 and half. Okay, total will be 2 and half, which is equal to S. And 2 into 2 and half plus 1. So if you cancel this, it will be, I think, yeah. I'm sorry. So it will be equal to, this is 2.5 into 2, 5, okay, plus 1. So total will be 6, okay. So, and J value will be, this is S, so 2.5, and here the L value, this will be plus 2, this will be plus 1, 0, minus 1, minus 2. So total, if you make the sum of this, it will be equal to 0. So if it is 0, the L value will be capital S. Okay. So 6 and S and J value. So total is 2.5 plus L value is 0. So total 2 and half. Okay. So highest, least the J value will come from the L plus S minus, then L plus S minus 1, then L plus S minus 2 up to L minus S level. So this is the least value. Okay. So in this way we can calculate the J value also. Okay. So for your examination, this up to this is enough. J is not mandatory. So up to this is so wherever the all the electrons, if they are half filled, it will be S term with the highest multiplicity, that is what 6. Okay. So it is sextet S. Okay. So the term symbol will be, ground state term symbol will be this. Okay. Now we'll cross check. Manganese. So I think plus 2 will not be there. So it is there. So this is not. Manganese in place 2 condition. So 2.5, it is 5 by 2, that is what. So this is. So you can apply the same method for all the elements and all the configuration, and you can cross check. Okay. So I hope you understand. So by understanding this, it is not enough. You must apply for 1 or 2 complexes or 1 or 2 elements and cross check. Then you will get the perfection. Okay. Thank you.